Good morning, everyone. Today we will be discussing some of the forces affecting conformation in biological molecules. Wherever there is a force, we think of energy as well. The stronger a particular force is, the larger is the energy difference associated with the movement with or against that force. Therefore, all of these forces affect the energy state of the biomolecules. It is important to understand that biomolecules run the gamut from molecules that are made up of only a few atoms to relatively enormous macromolecules that are made up of literally thousands or tens of thousands of atoms. As a result, particularly in the larger molecules, it is possible that many different forces can come into play at the same time. All of the forces we will speak about are electronic in nature, that is, they ultimately involve the interaction of positive and or negative charges. These forces manifest themselves in a larger variety of ways, and we classify them as different forces in order to categorize them according to their different behavior. Molecules are atoms connected together. The bonds that connect atoms together in molecules are called chemical bonds. There are, however, many types of bonds and forces that influence the exact location of the atoms within a molecule and so influence the conformation or shape of the molecule. But we need to first understand chemical bonds, since chemical bonds provide the primary structure of molecules. A chemical bond between two atoms always involves one or more of the outer electrons of the atoms. These outermost electrons that participate in chemical bonding are called valence electrons. There are two main types of chemical bonds. A covalent bond occurs when one or more of the valence electrons from each atom are shared between the two atoms, while an ionic bond occurs when one or more of the valence electrons are completely stripped away from an atom and are donated to the neighboring atom. Sometimes the electrons in a covalent bond may not be equally shared by both atoms. One of the atoms may have a stronger pull on the electrons than the other. This can be because one atom has a more positively charged nucleus or because its nucleus is more exposed to or closer to the shared electrons. When this happens, the electron cloud of the shared electrons leans closer to the atom with a stronger pull, giving that atom a slightly negative charge. The other atom will have a slightly positive charge. In such a case, the covalent bond is said to be polar, meaning that the electric charge is not evenly distributed across the bond. Covalent bonds typically have various amounts of flexibility. This flexibility, depending on the particular bond, can allow for movements such as free rotation, like a wheel and an axle, and spring-like movements such as bending, compression, extension, and twisting. This figure shows the types of movements commonly found in chemical bonds. We have the free rotation, bending, compression, extension or stretching, and twisting. Motions B through E are all spring-like motions. They occur with a restoring force, a force that somewhat opposes their motion and tends to restore the atoms back to their original position. So there are several types of chemical bonds. covalent bond, ionic bond, hydrogen bond, and metallic bonds. A lecture video on hydrogen bond and metallic bond is given in a separate video. All of the forces that affect conformation in biomolecules are electrical in nature, meaning they result from attractions or repulsions between charges. The force between two electrostatic charges is defined by the Coulomb's law, F equal to Ke times Q1 and Q2 over R squared, where F is the force, Q1 and Q2 are two charges, R is the distance between the two charges, and Ke is the constant. In SI units, Ke is equal to 8.98755 by 10 to the power of 9 Newton meter squared per Coulomb squared. The constant Ke is also equal to 1 over 4 pi epsilon naught, where epsilon naught is a constant known as the permittivity of a vacuum. In biophysics, we are most often interested in the amount of energy or potential energy resulting from molecular forces. This is because potential energy resulting from a force is that force's contribution to the Gibbs energy of the molecule. And it is the Gibbs energy that drives biophysical processes. Since potential energy is the potential to do work, and work is force times distance, we can write its potential energy as Q times Q1 over epsilon times R, where U is the potential energy, Q1 and Q2 are two charges, R is the distance between the two charges, and the epsilon, which is the permittivity of the vacuum, of the medium rather. The permittivity, or the epsilon, is called permittivity and is a measure of how easily a medium is polarized by an electric field. Epsilon is also called dielectric constant of the medium. Now consider a positive and negative charge in a vacuum and in a medium of high permittivity. The neutral but polar molecules of the high permittivity medium, such as water, orient themselves with their negative ends facing the positive charge and their positive ends facing the negative charge. This orientation of the polar molecules creates small electric fields that oppose the electric fields of the positive and negative charge in the medium. This effectively reduces the force and potential energy between the positive and the negative charge. The other type of forces are the dipole forces. It could be charge dipole, dipole-dipole, or induced dipole forces. An electric dipole is defined as two equal and opposite charges separated by a fixed distance. Just as amount of charge is a convenient way to characterize an ion, a convenient way to characterize a dipole is by a quantity called the dipole moment. The dipole moment is equal to the magnitude of the charge at one end of the dipole times the fixed distance between the two charges. Suppose we have a neutral but polar molecule. We can represent this molecule as a dipole of two opposite charges, Q plus and Q minus, separated by a distance L. The potential energy between an ion or point charge and the dipole is simply the sum of the potential energy between the ion and each of the charges Q plus and Q minus in the dipole, where R plus is the distance between the ion and the positive end of the dipole, and R minus is the distance between the ion and the negative end of the dipole. Instead of two separate distances, R plus and R minus, we introduce only the distance between the ion and the center of the dipole R. And since the charges on the dipole are equal and opposite, we replace Q plus with Q and Q minus with negative Q. So we can now write the potential energy between a charge and a dipole in this form. We can simplify this equation even further in the case where L is much less than R, making the potential energy in this form. In the previous equations, we assume a fixed orientation of the dipole with a charge. The angle alpha is assumed constant. This is a safe assumption in many situations, for example, in the case of a relatively inflexible folded protein molecule, where a dipole on one part of the molecule interacts with a charge on another part of the molecule. But in a situation where the alpha is on one molecule and the charge on another, and the molecules are in solution, then the dipole can freely rotate in solution. This is where thermal averaging comes in. It accounts for the random motions of molecules in solution due to thermal energy. In such a case, we have to use the average potential energy, average over all possible orientations. If we assume that the dipole moment times the potential energy is much less than kT, then the above sum can be calculated in its new form. Next interaction is dipole-dipole forces. When two dipoles interact, we have a total of 4 charges interacting, as compared with 3 charges in the case of a point charge and a dipole. When two dipoles interact, there are 2 different angles to consider for each dipole, as compared with a single angle to consider in the orientation between a point charge and the dipole. There are 2 considerations in the dipole-dipole interaction. Number 1 is each dipole can orient itself toward or away from the other dipole. The second one is that each dipole can turn to the right or left, clockwise or counterclockwise relative to the other dipole. So the potential energy between two dipoles is written in this form, where F is some function of the 4 angles alpha 1, beta 1, alpha 2, and beta 2. Subsequently, the thermal averaging in dipole-dipole interactions is written in this form. It is important to note that because of the higher power of radius r in the denominator, dipole-dipole potential energy can indeed be significant, but only at very short distances. Another dipole interactions is the induced dipoles. The electron cloud of a neutral, nonpolar molecule can be distorted in the presence of an electric field so that the molecule becomes polar. This is called an induced dipole. The electric field that induces the polar quality of the molecule typically comes from a nearby ion or dipole. We can measure the tendency of the electron cloud of an atom or molecule to be distorted from its normal nonpolar shape by an electric field. We call this measurement polarizability alpha sub p, defined as the ratio of the induced dipole moment to the electric field strength. Notice what this equation says. A large degree a large degree of polar a large degree of polarizability means a given electric field induces a large dipole moment. A small degree of polarizability means the same given electric field induces a small dipole moment. Please take note that alpha sub p is the symbol for polarizability and not alpha as the angle between a dipole and a point charge. Now we recall the standard formula for the strength of an electric field due to a point charge that is given in this form, where E is the electric field strength, Q is the amount of charge, epsilon is the dielectric constant of the medium, also called the permittivity, and R is the distance from the point charge. We then use it to write the formula for the dipole moment of an induced dipole. Subsequently, we write the potential energy due to the interaction of a charge with an induced dipole in this form, with the assumption that the dipole will orient itself in the direction of the charge. So that's it for now. Again, a lecture video on hydrogen bond and metallic bond is given in a separate video. So once again, thank you so much for your time.